Hi, this is In-Hwan Bae. In this video, I am presenting the Universal Trajectory Predictor designed to excel in any trajectory prediction task. The goal of predicting human trajectories is to infer socially acceptable paths based on previous steps. This is a crucial function for a variety of applications, including self-driving cars, delivery bots, urban development plans, robot navigation systems, and surveillance systems. To predict the future paths, the model initially observes all pedestrians in a scene. The model then analyzes the past movements and interactions between pedestrians to predict the trajectories for the next 12 frames. Under this basic setting of predicting the future, trajectory prediction have been adapted and utilized across various applications. Specifically, there are 5 distinct types of trajectory prediction tasks, each designed for different scenarios. First, the stochastic prediction task predicts all possible future modes of the pedestrian's movement to assess every potential risks. Second, the deterministic prediction task identifies the most probable path a pedestrian will ultimately choose. Third, the momentary observation task rapidly predicts future movements from just 2 frames, which is useful in emergency situations where the pedestrian appears suddenly. Fourth, the domain adaptation task evaluates performance in another to measure transferability and after training in one location. Last, the few-shot learning task adjusts the model's data efficiency by evaluating its performance with limited training data. Naturally, to effectively handle these specific tasks, specially designed models have been proposed. In particular, the introduction of new modules and the design of loss functions tailored to each scenario have significantly enhanced performance. However, this raises an important question. Given that all 5 tasks fundamentally involve predicting pedestrian movements, could a single general model that effectively captures human motion dynamics work well across all these tasks? Therefore, we propose a singular trajectory, a universal trajectory predictor that excels across all tasks. Our core concept involves projecting any given input and output path into a unified space from which predictions are made. This method ensures our model's adaptability and effectiveness in various situations. To begin, we apply singular value decomposition to all our training data to extract key motion features. Here, the singular vectors are the key components representing motion characteristics. Next, we use these key motion features to design embedding space. Since the singular vectors are orthogonal, they can be used as a basis vectors for a coordinate system. Thus, we define this coordinate system as singular space, where each axis corresponding to a singular vector. To facilitate a clearer understanding of the formulas, we denote coordinate in singular space using a script notation. Next, we introduce a projection method that enables predictions from any inputs and outputs. Based on the assumption that human motion dynamics are smooth, we use B-spline basis function to interpolate our basis vectors. This approach allows our singular space to be universally applied, adapting seamlessly to any trajectory length or type. For the prediction page, we introduce an adaptive anchor. Like conventional methods, we start by defining prototype anchors through k-means clustering of the training dataset. The traditional anchor-based method applies the same trajectory anchors uniformly across all pedestrians without personalization. We advance this approach by incorporating neighboring information to adjust the anchors, personalizing them to the traversable area. Lastly, we refine these initial anchors using a diffusion model. Similar to image generation, the conventional trajectory diffusion model begins with noise and incrementally denoise it step by step to converge toward the ground truth path. Here, since we have an initial path of an anchor, we design a diffusion process that starts from this anchor to the actual path. This design greatly simplifies the prediction processes by providing the model with an initial rough path. As a result, the model can generate realistic trajectories that accurately mirror motion dynamics, even when working with a limited number of learnable parameters and minimal training data. We evaluate our model by comparing it with current state-of-the-art models. We spatially test against the challenging momentary observation task and few-shot task. Our model significantly outperforms the existing leading models, including the latest diffusion-based and anchor-based models, showcasing superior precision and performance in these demanding conditions. And we quantitatively evaluate our model. Our singular trajectory model achieves state-of-the-art results across all tasks. Thank you for your interest in our work. Our codes are available online.